Just kidding. Now we have activation functions to go through. With this first video, I'm just going to do a couple of them, which would be Relu activation function, as well as sigmoid, which we'll be using for this first project, and then we'll expand to others, notably softmax, possibly some others. But yeah, here we go. So we'll make a new class for Relu. Just have an init. Which will have number of samples and the number of neurons. Have a forward, which will take the inputs and a backward to back propagate d values. And the num samples and number of neurons here is so that we can allocate the output layer, and the derivative of the inputs and stuff like that. Which will make the output the layer inputs, just copying the inputs, and the derivative of the inputs. Allocate memory, of course. And next we'll do the forward function. Yeah, kind of. I guess I would expect most people would know what a Relu activation function is, but basically, out of the previous, you would have a dense layer output, which we would need. with the Relu activation, you can take the dense layer output and makes it nonlinear by, if it's less than 0, then you make it 0. Anything greater than 0, keep it as is. Very simple one, and that's why it's used a lot. Easy. It's fast calculation and fast for the back propagation as well. So yeah, it's pretty simple. You go through each of the values. Of the inputs, and you'll take the max of it or 0. And might as well at the same time create the layer inputs copy. Okay, so we'll try that one out. So we did a forward through the layer dense. We'll also make this Relu. Call it Relu. Samples, neurons. And we'll take the previous layer's output as the input. And then we'll go ahead and print the Relu function's output as well. Make a difference. Okay, so got the first one, which is the outputs of the dense layer, and everything positive stays positive, but once you hit a negative value, it switches to 0.